Hi guys, welcome back to chemistry with Miss Hernandez at La Jolla High School. We're working on today's section 5.2 on your packet. We're talking about wavelength and frequency calculations, and we're using the information from our packet CK12. So this information that you see here will be on the Pear Deck that you see in front of you in the PowerPoint. Okay. So today we're going to be talking about wavelength and frequency. There is a big connection between the two, and we're going to talk about all of those topics. All right. Do you enjoy going to the beach? I know I do. Everybody that I know of loves going to the beach. It is, it's a fun, relaxing environment. All right. So who's going to help me read this section right here?
During the summer, almost everyone enjoys going to the beach. They can swim, have picnics, and work on their tans. But if you get too much sun, you can burn. A particular set of solar wavelengths are especially harmful to the skin. This portion of the solar spectrum is known as UVB, with wavelengths of 280 to 320 and sunscreens are effective in protecting the skin against both the immediate skin damage and the long-term possibility of skin cancer.
Thank you, Alexia. No. So all of us have been to the beach and maybe we're having too much fun with our friends that we forgot to put some sunblock or sunscreen, right? I don't know. Probably all of us are guilty. I know I'm guilty. I've gotten a really bad skin burn or sunburn. Not, and it wasn't as bad that I got, I don't know how it says, welts, or where you see that little bubble form because it's so bad. But I know my cousin did. He got stuck out on a boat and he decided to take off his shirt because he was so hot. And all of a sudden, a couple hours later, he's got big old ugly burns on his back. Okay. I think he even got third-degree burns. All right. So guys, make sure that you're always protected. Even if it's a cloudy day, you can still get a really, really bad sunburn. Okay, so be careful with that. All right, so waves. Anytime that UV light is coming through, or is being broadcast from the sun, it's moving in waves, right? And the waves you see are here, okay? And when it comes to UV, it's in nanometers, so you have very short waves, okay? The shorter the wave, the more dangerous the wave is. So waves are characterized by their repetitive motion. So imagine if a toy boat riding the waves in a wave pool. As the water wave passes under the boat, the boat's going to go up and it's going to go down in regular and repeated fashion, right? While the wave travels horizontally, the boat only travels vertically up and down. The figure below shows two examples of waves, okay? So here you have picture A. Picture A tells us or identifies the different parts of the wave, okay? A wave consists of alternation, crest, and troughs. The wavelength lambda is defined as the distance between any two consecutive identical points on the waveform. The amplitude is the height of the wave. All right, so here you have what's known as the crest. The crest is always the top curve of a wave. The bottom curve, the low curve, is known as a trough, okay? And amplitude is always from this 0 point line up to the top of the crest, or from the 0 point to the bottom trough. Wavelength they describe as being from one crest to the next crest. That is one full wavelength. Okay, so then you have in picture B, a wave with short wavelength on top has a high frequency because more waves pass a given point at a certain amount in a certain amount of time. Now on the bottom, you have a longer wavelength that has lower frequency. Okay? So here on top, the top picture, you have very short waves, okay? And anytime you have short waves, frequency is going to be high. If you have long waves, frequency is always low, okay? And then here's a better picture. Remember the top curve. The top curve is a crest. The bottom curve, the is the trough. And remember, if you are from one crest to the next crest, to the neighboring crest, that is one wavelength, okay? Amplitude can be from the 0 point, which is the black line, to the top of the crest, or the 0 point to the bottom of the trough, okay? That is amplitude. That is how high your wave goes, okay? All right, time to recall, time to remember. It says draw a wave with a very high frequency in red, draw a wave with a very low frequency in blue. Okay? What do you remember from the last slide? If you have high frequency, do you have long waves or do you have short waves? When you have low frequency, again, long waves or short waves? Draw it out. Maybe you can remember and give me a really good drawing. I'll give you about a minute. It's 31 now, so when it turns 32, I'm going to show your pictures. And I expect everyone to be drawing. I expect everybody to be drawing. All right? You got less than a minute. All right, so it is officially 1 minute has passed by. And let's check out your drawings, okay? Only 2 people drew. We can do better, but that's fine. One line. Come on, guys. You're supposed to draw waves. What happened here, guys? You're supposed to be drawing waves, not lines. Waves. Nobody drew a wave? Want to try that again? All right, let's try again, guys. Remember, you're supposed to draw a wave. A wave. Either long waves or short waves. Which one will have high frequency? Which one will have low frequency? Okay? Try it again. See if you guys can get that. Hey, Caitlin, I'll change your attendance in a second. All right, let me do it now. Irvin was here. He's having trouble with his internet, so Caitlin's here. Okay, there we go. All right, let's see if we can get a better picture now. Oh, there we go. Very good. At least now we're seeing waves. What happened? Okay, now remember, if you have high frequency, you're going to have very short waves, okay? In low frequency, you're going to have very long waves, okay? And we're going to go back and we're going to see a picture. Okay? Short, it should have done in red, right? The short waves, and in blue, you should have done the long waves, okay? This is what I was looking for, guys. A picture that looks like this. Okay. So you should have had very small in red, very small and short waves, and then long waves in blue. All right, this one's an easier one. Drag your yellow circle to a crest. Where do I have crests on these waves right here? Where's the crest? And then drag your green circle to a trough. And we talked about examples of both of those. Okay, I'll give you a minute. At 36, you got 1 minute. It shouldn't take you 1 minute, but I'll give you some time. Where is the crest? Where is the trough? In any of these two waves, any of them. You can do the pink wave or you can do the blue wave. It doesn't matter. Drag your circle to a crest. Drag your green circle to a trough. Yellow to a crest, a trough in green. Only 2 people are answering. Are we paying attention? If you want to join me in the pair deck, Caitlin, it's right there. Only 2 people. Come on, guys. I should have 5 people participating. Where is the crest? Where is the trough? All right. Remember, the crest is the top of the wave, this top curve right here. This is a crest. The yellow circle should have been up here, okay? And I can't do it for you. Uh-oh, what happened? All right, the crest is always the top of the curve. The top of a curve or the top of the wave. The trough is the bottom. Very good. Whoever's moving that yellow button, that's good. The trough is the bottom curve. This bottom curve. All of these bottom curves are troughs. Okay? Move your green button to a trough. There you go. There you go. Right there. That is a trough right there. Great. Leave it there. Leave it there. You're good on that green one. Perfect. All right. Excellent. A wave. A wave. A wave cycle consists of one complete wave starting at the 0 point, going up a wave. Okay, so a 0 point is the black line, right? This is the 0 point. So if you start here, you go up the crest, down to the trough, and you go to the 0 point again. That is one wavelength, okay? That's one wavelength. The wavelength of a wave is the distance between any 2 corresponding points on adjacent waves, okay? The easier way that I do it is crest to crest or trough to trough. That is easier for me, okay? I see the wave a lot easier if I start at a crest and I stop at the next crest. Or if I start at the trough and end at the next trough. That is one wavelength, okay? In an equation, wavelength is represented by the Greek letter lambda, which kind of looks like a TP or an upside down Y. Depending on the type of wave, wavelength can be measured in meters, centimeters, or nanometers. And if you need the conversion, 1 meter is equal to 10 to the 9 nanometers, okay? The frequency represented by the Greek letter nu is the number of waves that pass a certain point in a specific amount of time. Typically, frequency is measured in units of cycles per second or waves per second. I personally like the waves per second. It's easier to understand. 1 wave per second is also called a hertz. Okay, if you have 1/s, that is hertz, okay? And that's kind of saying like s to the negative 1 or Hz for hertz. Figure B. Figure B shows an important relationship between the wavelength and frequency of a wave. Okay, so here's the relationship. The top wave clearly has short wavelength, uh, has a shorter wavelength than the second wave. However, if you picture yourself at a stationary point watching these waves pass, more waves of the first kind would pass in a given amount of time. Thus, and here's the relationship, frequency of the first wave is greater than that of the second. So wavelength and frequency are inversely related, meaning if one goes up, the other is going to go down. Okay. So if I have length, if I'm talking about length and I'm getting longer and longer and longer, my length is increasing, frequency is going to be low. So if length goes up, frequency goes low. If the length is decreasing, it's getting shorter and shorter. If the length is going down, frequency goes up. Okay? That one will go up, the other one will, because the other one went down. We call that an inverse relationship. Inverse relationship just means if one goes up, the other goes down. If one goes up, the other one goes down. And this the what we're talking about, what's going up and what's going down is length. If the length is getting longer, frequency goes down. If the length is getting shorter, frequency goes up. Okay? As the wavelength of a wave increases, frequency decreases. The equation that relates the two, speed of light, the variable the letter C is the speed of light, luz, right? The speed of luz, how fast light travels. Okay, for the relationship to hold mathematically, if the speed of light is used in meters per second, the wavelength must be in meters and frequency. Okay, so anytime you have nanometers, you're gonna have to change nanometers to meters. Okay, and you usually have to divide. Okay, and I'll show you an example right now. All right, you got a true and false question, and I expect everybody to participate in this question because it's a true and false. Very, very easy. The variable C. The variable C is speed of time. True or false? True or false? Pick one, guys. Is C the speed of time? And I just talked about this variable. Okay, I just talked about it. Is the speed of time the variable C? True or false? And if you're not in the pair deck, you should be answering in the chat. This one you can answer it in the chat. Only one person has responded. What about the rest of you? Come on. This is ridiculous. Come on, guys. Help me out. Caitlin, true or false? America, true or false? What do you think? Francisca, Melissa, true or false? What do you think? Is C the variable C speed of time? America thinks it's true. Anybody else want to take a crack at it? 3 people have voted. 3 people have said it's true. Oh, guys, let's go back. Look over here. What does it say for the variable C? Speed of light. That is a false statement. Very good, Mario. That is a false statement. Very good. Speed of time is not the letter C. Very, very good. Okay. The answer should have been false. False, guys. All right. We have a sample problem. The color orange within the visible light spectrum has a wavelength of about 620 nanometers. What is the frequency of the orange light? Okay. The first thing you need to do is you need to find out what you know. We know that wavelength is 620 nanometers. We know the speed of light is 300 million, which is 3 times 10 to the 8th meters per second. And if I want to convert nanometers to meters, I need 1 meter is equal to 10 to the 9 meters. All right. So guys, come back to the Google Meet. I'm going to show you on Jamboard how to do this. All right, here I have Jamboard. I'm going to be writing with a black pen or black marker. Now, the first thing I need to do is I need to convert. I need to convert 620 nanometers. Okay, and I'm going to use this information right here to change nanometers to meters. Okay, so I have 1e to the 9 nanometers is equal to 1 meter. All right, nanometers cancels. Now the only thing that's left to do is to run the math. Okay, so I'm going to get a calculator, right? I'm going to get my phone and ignore the messages that are there, and I'm going to go straight into my calculator, and I'm going to put 620. And what am I going to do? What am I going to do here if they're on opposite sides? What do I do? Multiply or divide? What do you remember if they're on opposite sides of our square? Anybody remember? What am I going to do? Multiply or divide if they're on opposite sides? I'm looking at the chat. Nobody has told me what to do mathematically. Melissa says multiply. Okay, Melissa, remember, they both have to be on top in order to multiply. So if I got top and bottom, what do I do if I got top? Divide. Excellent. All right, so I'm going to hit divide. I'm going to put my phone to the side so that I can do scientific notation. 1e to the 9 gives me a very small number. Look at that number. Very, very small. Okay. So my answer is I'm going to change it to scientific notation, which is 6.2e. And then I'm going to count how many times I'm going to get to that 0 or to get to that 6. 1, 2, 3, 4, 5, 6, 7. I am moving my decimal 7 times so that I can change it to meters. Okay, this is what I need. Okay, now this formula, the formula speed of light is equal to lambda times frequency can be put in the triangle that we use for density, where the speed of light is on top, frequency is on the left, and wavelength is on the right. Okay, now that I have this information, I can input my numbers. Okay, I know the speed of light. The speed of light is 3e to the 8th. 3e to the 8th. They're asking me for frequency. So I'm going to put my number that I got on the right. 6.2e to the negative 7. And this just means, remember, if you're on top and bottom, you're going to divide. Okay? So I'm going to get my calculator again. I'm going to zero it out. 3e, remember the double E, right? The double E is your friend. And then I'm going to put 8. And I'm going to divide 6.2e to the 7, and it's negative. Look at how big that number is. Look at how big that number is. That's a huge number. If I wanted to change it to scientific notation, 4.8 times 10 to the negative, times 10 to the 14. All right, so frequency, letter V, is equal to 4.8 E to the 14th hertz. Now, if we had our regular schedule and we were back in school and we had a block scheduling, we would spend a whole day learning how to do this. Okay. We're not, right? We're not in school. I don't have time. We only have one period actually to cover this. And I thought they were going to give us 2 days to discuss calculations. It's only today. Okay. So we're going to skip. We're going to go back to the pair deck. I'm going to go back to the pair deck. Let's look at the answers they got. All right. So the first thing we did is we converted. We got this number that we got 6.2 e to the negative 7 meters. And then I took the speed of light. I divided it by the answer from the first one, which is the same thing we did, right? We divided and we got the same answer 4.8 e to the 14 hertz. Excellent. Excellent. Okay. We don't have time for you guys to try this on your own. Okay. I think it's a little too hard. Let's watch this video.
Hey guys, it's Science Made Easier, and today I am going to show you how to find the wavelength or frequency when given the other. So let's start by looking at this triangle equation and defining the variables real quick. So c is your speed of light. This is a constant. It will never change. It will always be 3.0 times 10 to the 8th. V is your frequency, which is represented in hertz or seconds to the minus 1. Lambda is your wavelength, and it can either be in meters or nanometers. It is usually in nanometers, though. So using this equation, you can substitute whatever you're given in that problem and find whatever you're not given. So let's try it in a problem. So let's say you have this problem. Light with a frequency of 7.26 times 10 to the 14th hertz lies in the violet region of the visible spectrum. What is the wavelength of this frequency of light? So we're looking for wavelength. So let's go back and look at the equation real quick. So if we're looking for lambda, which is wavelength, we have c over v. So we're going to divide the speed of light by our frequency. So let's go back to this problem real quick. Since we know what we're doing now, let's actually do it. So we're going to divide the speed of light by our frequency that we were given. So the speed of light is 3.0 times 10 to the 8th. We're going to divide that by our frequency, 7.26 times 10 to the 14th. And that leaves us with 4.13 times 10 to the negative 7th. So since I said that nanometers is what it's usually in, we're going to convert from meters to nanometers. So all we have to do to convert from meters to nanometers is multiply by the conversion factor. So 4.13 times 10 to the negative 7th times the conversion factor, which is 10 to the 9th nanometers over 1 meter, which will give you 413 nanometers. So let's try another problem. So say you have this problem. Calculate the wavelength of radiation with a frequency of 5.00 times 10 to the 14th seconds to the minus 1. So seconds to the minus 1 is the same thing as hertz, so you can just kind of disregard that. We're finding wavelength once again, so it is the speed of light divided by your frequency. So let's do that. So 3 times 10 to the 8th divided by your frequency.
All right, we're going to stop there. Okay. I don't want to run out of time. Okay, so let's head on out of here. Let's summarize the topic. Summary. All waves can be defined in terms of their frequency and intensity. C. So you have your equation. C equals to lambda times, or wavelength times frequency. Speed of light is equal to lambda times frequency. Expresses the relationship between wavelength and frequency. And then you have your review questions. They're really, really short. It says number one, define wavelength. Number two, define frequency. Number three, what is the relationship between wavelength and frequency?